Hello everyone, welcome to Explore Hop. For this example, we're told to use the key features of the function below to sketch its graph. Label all x-intercepts, stationary points, and inflection points. And the function we're given is the function f of x equals x cubed minus x squared minus 2x plus 2. First, let's start by finding the x-intercepts of this polynomial. To find the x-intercepts, or roots, of this polynomial, we need to set f of x equal to 0. So if we set f of x equals 0, we get that x cubed minus x squared minus 2x plus 2 is equal to 0. From here, we can factor this polynomial by grouping. So factoring out an x squared from the first two terms and negative 2 from the last two terms, we get that x squared times x minus 1 minus 2 times x minus 1 is equal to 0, which means that x minus 1 times x squared minus 2 is equal to 0. And this means that x is equal to 1, negative root 2, or positive root 2. And this gives us the roots, or x-intercepts, of this polynomial. Now let's find the stationary points of f of x, which occurs when the derivative of f of x is equal to 0. So using the differentiation rules we've learned, the derivative of f of x is equal to 3x squared minus 2x minus 2. And setting the derivative of f of x equal to 0, we get that 3x squared minus 2x minus 2 is equal to 0. And this quadratic polynomial is not factorable, so we will use the quadratic formula, which means that x is equal to 2 plus or minus the square root of negative 2 squared minus 4 times 3 times negative 2 all over 2 times 3, which is equal to 2 plus or minus the square root of 4 plus 24 all over 6. And this is equal to 2 plus or minus the square root of 28 all over 6, which is equal to 2 plus or minus 2 root 7 over 6. And dividing the numerator and denominator by 2, we get that this is equal to 1 plus or minus the square root of 7 over 3. So this means that x is equal to 1 minus root 7 over 3, or 1 plus root 7 over 3, which is approximately equal to negative 0.55 and 1.22. And f of 1 minus root 7 over 3 is approximately equal to 2.63, and f of 1 plus root 7 over 3 is approximately equal to negative 0.11. So this gives us the stationary points. Now we can use the stationary points we found to find the increasing/decreasing intervals. We can set up a table in order to determine the intervals where the derivative of f of x is positive and the intervals where the derivative of f of x is negative, because that will indicate whether or not f of x is increasing or decreasing. So let's construct a table. Here is what the table looks like. From the stationary points, we will check whether the derivative of f of x is positive or negative in the intervals from negative infinity to 1 minus root 7 over 3, from 1 minus root 7 over 3 to 1 plus root 7 over 3, and from 1 plus root 7 over 3 to infinity. And to determine the sign of the derivative in an interval, we can sub a value of x in the interval into the derivative of f of x. So if x is in the interval from negative infinity to 1 minus root 7 over 3, then we can sub negative 1 into the derivative of f of x. And we get that the derivative of f of x is positive. And now we do the same thing for the other two intervals. If x is in the interval from 1 minus root 7 over 3 to 1 plus root 7 over 3, then we can sub x equals 0 into the derivative of f of x, and we get that the derivative is negative. And if x is in the interval from 1 plus root 7 over 3 to infinity, then subbing in x equals 2 tells us that the derivative of f of x is positive. And we can also represent this information on a number line. So if we construct a number line, the derivative of f of x is positive in the first interval. So f of x is increasing in this interval. Negative in the second interval. So f of x is decreasing in this interval. And positive in the last interval. So f of x is increasing in this interval. Now, let's find the intervals of concavity. Before we find the intervals of concavity, we first need to determine the points where the second derivative is equal to 0. So using the differentiation rules we've learned, the second derivative of f of x is equal to 6x minus 2. Now, we set the second derivative of f of x equal to 0. Which means that 6x minus 2 is equal to 0. So 6x is equal to 2. And x is equal to 2 over 6, which is equal to 1/3. Now, we can set up another table to find the intervals of concavity. Here is what the table looks like. Since the second derivative is equal to 0 at x equals 1/3, then this gives us two intervals to check. We will check whether the second derivative is positive or negative in the intervals from negative infinity to 1/3 and from 1/3 to infinity. And once again, we sub a value of x from each interval into the second derivative of f of x. So if x is in the interval from negative infinity to 1/3, then subbing in x equals 0 means that the second derivative of f of x is negative. And if x is in the interval from 1/3 to infinity, then subbing in x equals 1 means that the second derivative of f of x is positive. And we can also represent this information on a number line. So if we construct a number line, the second derivative is negative in the first interval, and it's positive in the second interval. This means that f of x is concave down in the first interval and concave up in the second interval. Now let's find the local max and min points. From the stationary points we found earlier, since 1 plus the square root of 7 over 3 is greater than 1/3, then the second derivative at x equals 1 plus root 7 over 3 is greater than 0 from the information above. So this means that f of x has a local min at x equals 1 plus root 7 over 3. And since 1 minus root 7 over 3 is less than 1/3, then the second derivative at x equals 1 minus root 7 over 3 is less than 0. So this means that f of x has a local max at x equals 1 minus root 7 over 3. And for inflection points, we can see that the concavity changes at x equals 1/3, since the function goes from concave down to concave up. So f of x has an inflection point at x equals 1/3. And f of 1/3 is approximately equal to 1.26. Now, putting everything together, this is what the graph of the function looks like. Take a moment to study this graph and see if you can verify the intervals of increase and decrease and the intervals of concavity that we found. And that's it for this example. Thank you for joining us. See you in the next lesson.